is with North Carolina State University, degrees from Rensselaer Polytechnic, postdoctoral work here in Washington, and been at NC State since 2010. And so with that, please, Aranya.
Thank you.
Again, and you can tell this is a very interested audience. So, you know, the more time you can save for questions, the more conversation we're going to have. So, all right.
Thank you, Joe. Thanks for the introduction. And again, I wanted to thank Brian and all the other organizers for inviting me. This is turning out to be an absolutely fantastic workshop. I'm learning a lot of things, and I'm very excited to be here. So, as Joe said, that you know, I come from North Carolina State University, and more specifically, I'm affiliated to the NSF Freedom System Center over there. And my personal background actually is from power systems and control systems. And this is a piece of work which I did with one of my power electronics colleagues at the Freedom Center. And it's very, you know, closely and strongly related to the theme of the workshop. So I thought that it might be beneficial to come over here and share these results with all of you. The specific kind of converter which I will be using for the purpose of this particular talk is the solid state transformer, or SSTs, which is sort of like the benchmark product of the Freedom System Center. But I just wanted to make a very big disclaimer at the very outset that all the control designs which I will be talking about are not specifically just tied to SSTs. They are applicable to any grid following voltage source converters, which are you know, more suitable for solar penetration, for example. Again, and another quick point before I get started is that the results which I will be presenting are for grid following converters, but then I wanted to make on my way, I will make pointers to you, all of you to point to the fact that what additional constraints need to be added on top of the results which I will be showing to transition from grid following to grid following. All right. So again, so just to get started, I guess, you know, this is more of like a motivational slide that, you know, in recent years, we have started seeing the concept of network microgrids to become very popular to guarantee resilience of the distribution system. And the solid state transformer is an excellent device which can facilitate the integration of network microgrids, distribution systems consisting of network microgrids to the transmission network, for example. And in this project, what we wanted to do is mostly primary control of network microgrids using grid following SSTs. And what that really means is that we want to regulate the DC bus voltages at the high voltage and low voltage phases, which constitutes the volt-watt control. And we also wanted to do current control or volt-watt control, essentially. And both of them kind of contributes towards primary control. The controllers which I will be showing to you guys, they are multivariable controllers, as a result of which implementation-wise, they will have some communication interpretations, which, you know, I wanted to specifically show to Rohi, you know, considering the communication slides that he was showing in the morning. So I look forward to showing those results to you guys. This is the system configuration of the power distribution system. So on the left, you have the legacy system, which is the transmission grid. And then on the right side, say, for example, you have a network of these microgrids. And I'm just showing, you know, one poster child for one of the microgrids on the leftmost side. So what you have is that you have the solid state transformer, or the SST, which converts the grid voltage from AC to DC. And then on the low voltage side, you have the low voltage DC buses where you can connect DC devices such as solar plants and energy storage devices, and also DC loads. And at the same time, the interesting thing about the SST concept is that you also have the provision of feeding AC devices on the low voltage side, for which you do another round of DC to AC transformation. And you can connect AC loads and wind power plants and other AC devices that you have on the low voltage side especially. This shows the circuit diagram of the SST concept. So again, so you have I'm showing kind of like in the DQ coordinates to facilitate the conversation, and it will become clear why I'm placing so much importance on the DQ frame in just a minute. So first you have this LCL filter concept, right? And then comes the inverter. Then you have the low voltage to high voltage, high voltage to low voltage transformation through the dual active bridge, or the DAB. And then on the low voltage side, you have the energy storage devices connected over there. And the control inputs, which the physical meaning of the control inputs, which I will be using for my designs, are the duty cycle of the inverters, also the phase shift of the dual active bridge, and the battery control, the battery current, which also will be regulated to its necessary set points. Just a quick overview. I don't know like how much this slide really speaks, but I still wanted to show the state variable model that we use for each of these SSTs, kind of reflective of the fact that we actually use detailed models. And the state variables over here mostly consists of the D and the Q axis currents of each stage, and also the control voltages of the different points which I showed in the previous circuit diagram. And I think the most important message from these state equations is that if you look at the right hand side of the state equations, majority of the terms look bilinear, which means that they're product of each of the individual states, and which kind of makes sense physically because each of the state equations is driven by power, and power is a product of current and voltages, right? So, which kind of makes this whole system overly nonlinear, especially for the input terms. Like for example, if you look at the terms involving the U variables, you will see that they are always multiplied by the states, which makes the overall system kind of bilinear. And that's where all the bifurcation and all the bad stuff starts happening when you put all of these things together at a larger scale, that the bilinearity kind of amplifies. However, I forgot to acknowledge this at the very first slide. So we had these two very capable students who helped us in deriving all these results. So Rafael was actually the main student who was driving this initiative. So he actually kind of jotted down the system equations and represented them in the so-called Port-Hamiltonian representation that we have seen a lot for passivity-based control designs on the transmission network, and also for isolated boost and buck converters. There are results by Astolfi and Romeo Ortega who have used these Port-Hamiltonian forms for proving stability of individual power electronic devices. But here what we are talking about is the network scale systems, although unlike the previous speaker, my network is radial, so it's a little simpler compared to the mesh network that he was talking about. But in any case, so we showed that the state equations can be represented conveniently in the Port-Hamiltonian form, where this big J matrix, has a certain skew symmetric structure, and R is diagonal, but still that's a nonlinear term because J is a function of the states itself. What is most problematic is the next term, which is Gx times U, which is the bilinearity which I was talking about, where your control input is multiplied by the system states. And so you have to be extremely careful about what kind of negative impacts it may have in improving overall closed loop stability. Just wanted to remind you guys of the control objectives again. So so we are over here. Right now, we are just trying to do primary control, which is balancing of powers according to set points which have been dispatched. And that boils down to regulating the low voltage and the high voltage DC voltages, as well as the current control, which contributes to the watts. Now, see what happened is that, okay, so this work was going on for some time in the Freedom Center, and PIs and the PIs who were working on these kind of projects, they were just using standard proportional integral type controls, which we have all learned in our undergraduate control courses. And now PI control works nicely. As I was having this conversation with some of my power electronics friends during lunch, that in power electronic converters, we always use PI control and it magically works, and there's no signs of instability without any proving theorems and things like that. But here what happened is that, this is again going back to the bifurcation discussion which was mentioned earlier in the morning. So what happened is that if I use traditional PI controllers, which are common in the SST literature, if the load fluctuates too much, which is becoming more and more common in the distribution grid anyway because of high variability of loads. So for certain operating conditions, if you linearize all those nonlinear equations which I was mentioning in the last slide, and for certain operating conditions, you can show that the eigenvalues of the linearized system actually start migrating towards the right-hand side, which means I have hub bifurcation essentially. Okay, so that's where I think the motivation for this design came in, that I don't want to rely on just local small signal models based PI control. I want to design a controller which is globally stabilizing so that I don't have to worry about load fluctuations and keeping on going back to my system and retuning all the PI gains so that I still have stability for that particular operating point and things like that. So that's the motivation that the proposed PI controller that I will be presenting does not need to retune any gains for any load variations because it's globally stabilizing. It admits that both advantage as well as disadvantage wise, I would say that it admits different communication topologies, which I want to mention in just a few slides. And the derivation is based on passivity theory and Lyapunov stability theorem. Now, before I actually mention the specific slide on why I'm using passivity, I think let me just motivate that discussion by saying that in the title I say that the proposed controller which I am going to design is a PI controller, despite my plant being a nonlinear plant. Now, how is that possible? How can you have a nonlinear plant and how can you still have a linear controller? Now, this concept actually has been very popular in control theory, where we do projections, we do appropriate projections on the nonlinear system and bring it down to a sort of simple looking plane where I can still design a linear controller, and the linear controller can stabilize the nonlinear plant. The upshot is that if you do those kind of transformations, then you lose controllability. Okay, so that the simplification of control design comes at the price of controllability. And here, I think the message is that if you can make use of system-specific properties, actual physical properties such as passivity, then you can still guarantee closed-loop stability despite having that loss of controllability factor. Now, the main tool that we make use of is actually what we call incremental passivity, which is a slightly less restrictive version of passivity. And what that really means is that you don't need to have your system passive globally, but you just need your system to be passive with respect to the operating condition over which it is linearized. Okay, so that's why that X star plays a very important role over here. And you just need your system to be passive, which means that I can find some storage function whose derivative is not less than y transpose u, y being the output and u being the input. But this v does not need to be for every region of the state space. It only needs to be with respect to the point of linearization, your previous powerful solution essentially. Okay, and that's and if you look at the structure of this controller over here, so I think this is where the entire message here lies, that the combinations of the terms are still in terms of bilinear, right? So there's voltage and current, but the overall structure is linear because I took advantage of the incremental passivity property to make one out of the two variables to be the star variable, which means that I'm considering the previous operating point and not just any global voltage and current signal. What does this mean? Well, this really means that the function V is the incremental energy with respect to your previous power flow solution, and that the rate of change of that incremental energy must be less than or equal to what is being generated. Essentially, you cannot produce more compared to what actually comes in. But what comes in is measured only with respect to what you had in the previous equilibrium. I think that's what the incremental concept actually means. By making use of these specific physical properties such as incremental passivity and designing DQ space, which makes the design linear. So we came up with this still linear looking multivariable PI controller. And again, I would like to reiterate the message that what is allowing us to have a linear controller despite my plant being nonlinear are these two properties. One is the DQ projection, which allows me to do the design in the linear space, but still guarantee stability for the nonlinear system. But despite the threat for losing controllability, I have passivity to save me in my final Lyapunov proof. Right, okay, so here is the multivariable PI controller where the Y bar again is not the absolute voltage, it's not the absolute output, it's the output measured with respect to what I had in the previous equilibrium. So you had a proportional term and an integral term, but you have to remember that because this is multivariable, the Kp and the Ki, these are matrices. These are not just scalar constants anymore. They are matrices, which kind of mean that the zero pattern or the sparsity pattern of these matrices decide which converters have to talk to each other. If these are dense matrices, that really means that I have an all-to-all communication needed from other converters to compute my control input. Okay, and if I can somehow promote sparsity, if I can promote some of the entries of these Kp and the Ki matrices to be zero, that means that I don't need feedback from those other inverters to compute my control gains. In terms of stability, all of this actually boils down to a ridiculously simple linear matrix inequality, which is really the high point of this design, that the design itself is not difficult at all. So the Kp and the Ki matrices just have to satisfy this LMI, which is pretty easy to solve. Again, in terms of communication topologies, it's the same thing which I mentioned just one slide before, that depending on the sparsity pattern of these two matrices, Kp and Ki, that kind of decides whether I need your output to compute my control input or not. And if I can make these matrices, say for example, if I make them block diagonal, that means that I go back to the completely decentralized implementation. That means that I don't really need any output feedback from any of the other converters to compute my control input. So the communication can be completely local in that case. So these are the three communication topologies which kind of follows from the construction of those matrices. If those matrices are dense, which means that there's no zero at all, that means there has to be all-to-all communication between all the SSTs, which kind of boils down to a centralized architecture implemented in a distributed way, but since it's all-to-all, then essentially it's centralized. If you can promote sparsity and still guarantee stability, if you can promote sparsity and still satisfy that LMI which I wrote over there, then you don't need all the SSTs to talk to each other, and that reduces the communication overhead a little bit. And if you can find out Kp and Ki matrices which satisfy that LMI despite being diagonal, then you are luckiest, because then you can guarantee stability by completely local control action, and you don't need feedback from any of the other SSTs at all. And so that's the diagonal formulation. And again, depending on operating conditions, depending on the set points, the star values, and the topologies that you have, it may be easy, it may not be easy. It depends completely on the system configuration. This is sort of the implementation diagram, and I think again the implementation diagram is interesting in the sense that it kind of tells me that my system has bilinearity, but I'm getting rid of the bilinearity by making one of the outputs as the star points essentially, which means that it's a constant. And that goes back to the incremental passivity idea, that I'm measuring everything with respect to the previous equilibrium. Scalability of communication. So how does all of this cyber physical architecture is going to work out in reality? And I specifically wanted to share this slide because I want to open up a discussion about where the distribution system operator, or where the DSO actually comes into this whole picture. And I guess the one idea can be that if we really have to make all of this network microgrid scalable, then we can divide them into these discrete regions, where each region has a supervisor of its own that computes the set points, those star values, by solving a distributed power flow. And generally, the distribution system operator do not want to interfere with individual converter level set points. So what they can do is that they can specify the constraints on the voltages and the currents that you have at the boundaries of each of these regions, which now needs to be a constraint on top of the power flow which is being solved by the supervisors in a distributed way. We did some simulations. I think the simulation was done on a 3 SST system, and the load was suddenly increased to unpredictably to 200% of its previous value. And by applying our multivariable PI controllers, we could show that with a reasonably good amount of transient performance, all the SSTs are being able to do primary control by tracking voltages and currents in the way that they are supposed to. This is a picture showing the trade-off between all-to-all and decentralized communication. Of course, both of them work, but what happens is that when you have the decentralized control, which is like completely local action, which means minimal amount of communication, the transient overshoot sometimes tends to go over the maximum allowed limit before saturation kicks in, essentially. So the red plot is the local control, and the blue plot is the all-to-all. So you can see that, you know, you gain a lot of communication overhead, but what you lose is transient performance, which may be a little bit deterrent in this case, because the control input was duty cycle, which cannot exceed 1. So of course, you know, if you go above 1, it will saturate and bring non-unity back into your system. And the last slide, I think, essentially is showing that if you, in this particular operating scenario, if you actually apply the conventional PI control and not the passivity-based, incremental passivity-based PI control that we propose, primary control completely fails, essentially. Okay. So the red curve cannot take you to the voltage and the current set points that you wanted at all, while the blue curve is successfully able to do so following our control algorithm. Conclusions, I think, again, so primary control of network microgrids with grid following converters so far. And, you know, if you want to add the grid forming component on top of this, then I think what will happen is that you have an additional constraint on angle and frequency synchronization at the individual inverter buses on top of those LMIs which I showed, essentially. Okay, so what we proposed is a globally stabilizing passivity-based PI controller, which does not need any PID controller tuning as operating conditions or load conditions change. 2 layers of communication is needed. One is the broadcast from the supervisor or the distribution system operator for communicating the set points for the currents and the voltages of the converters following from power flow back to the individual converters. And then the second layer of communication is a little bit more involved, which is peer-to-peer communication between the converters if you want good transient performance. And if you want to reduce that communication, then you have to remain satisfied with some bad transient performance, as was shown in that saturation plot which I showed. Again, so future work is that, okay, so this is not even actually future work, it's kind of like part of an ongoing work that when you have grid following to grid forming converter concept, then you have this additional layer of constraints of angle synchronization that needs to be taken care of on top of the passivity concept which I described. And more importantly, the scalability aspect, I think, you know, to me, it's a very important aspect that, you know, the workshop actually is talking, the roadmap which was shared by Brian as a part of the workshop, it literally said that millions of these DERs are going to infest the grid in very near future. And so if scalability, if we are really going to that level of scalability, then, you know, how do we solve region-wise distributed power flow and broadcast, and then converter to converter communication for actuating these kind of controllers? I think all of these need to be taken care of very, very carefully. And validation was done using we have a huge bunch of test beds in the Freedom Center, power system test bed, power electronics test bed, the hardware in the loop test bed using the Green Energy Hub and all that. So the hardware testing was done using those test beds. I guess with that, that's pretty much all I wanted to share. And this is my email address. If you have any questions at all, I'll be here for, of course, for the rest of the workshops. I'm very happy to talk to you in details. But if you have any questions, please email me. And that's also my research webpage. So I try to keep all of my papers and my reports and some simulation codes of MATLAB and Plex. They are also up there on the website. So if you're interested, please go ahead and check them out. And I think with that, I will say thank you very much for listening. Thank you.
We'll take a few questions now, won't you?
Thanks for the interesting presentation. So I had a question regarding, since you had scalability in the slide 10.
Mm-hmm.
So one of the questions is the means by which you're trying to tune the parameters in an N-microgrid scenario or NDER scenario seems to be based on an understanding of the exact model of the system.
Yes.
So how feasible is that in a large-scale system? Or even where there's sufficient penetration of DER? as one of the questions would be DERs might be within customer zones, so in which case you may not have enough information on the DERs in the first place.
Right.
The second question is they're often looking at what the line impedances,
Right.
estimating all these parameters.
Right.
So how feasible would you consider?
Yeah, it's difficult, but at the same time, nothing is magic, right? So things have to be done following the rules of physics, as we heard earlier. So I think what I was trying to say in this diagram is that, yes, I mean, within one region, which can be one residential neighborhood, as you said, you can keep things private. You can keep all the information about your admittance matrices and things like that private, which is just part of the supervisory controller number 1, for example, in region number 1. But then these supervisors need to exchange some amount of information to solve the power flow in a distributed way, to generate the set points. Otherwise, right? I mean, I don't really see any other alternative of how things can be done in a completely decentralized way without sharing any information with others at all, and still expecting the whole network, which is really connected to each other, to be stable. So I think that would be my first thought. But one important thing also I forgot to mention when I was talking about the design is that when you apply these very specific Port-Hamiltonian models based on distributivity and things like that, they have a certain amount of robustness that comes with it. Okay, and what I mean is that even if the computation of the set points is not exact, for a certain amount of time, like for example, if it takes a finite amount of time for the supervisors to carry on the distributed power flow to generate the exact value of the set points, during that period of time, the distribution network is operating on wrong set points, right? Like the previous set points, while the load has actually already changed. So there's a certain amount of robustness in these controllers which can sustain that. So it won't make you like instantly unstable or anything. So you can have a little bit of delay in getting the exact values of the set points.
So any thoughts on the fact that, like today's, for example, most systems that are integrated are based on this robust.
Yes.
And you can design systems by using set of other scripted. But if you're moving away from that concept, specifically with large generation, do you have any insights on the fact that how can we introduce robustness without trying to identify other DERs that we should?
Yeah, certainly. I think that's what I was actually trying to say, that if you don't want to utilize whole system level information, which actually may have a point, then even if you have a slightly incorrect values of set points, then the controller robustness can actually take care of that. I think that's what I was trying to say.
Other questions?
Yes, sorry.
So I guess I have a question that connects to your expertise at the bulk power system level. And maybe that's why your best place to answer this is, do you see the same density of communication at the distribution layer or the distribution system affecting similar or achieving similar performance as the bulk power system?
Yeah, I think the answer is yes, but the timescales are slightly different, because if you look at the timescale of the simulations which I was showing, right? So, the settling times and all these things, they are much faster compared to what we get at the transmission level when we see different mechanical oscillations, for example.
We've run out of time, so let's thank Aranya.
Okay. All right.